Hello, everyone. Welcome to this course again. So in this lecture, we're going to delve deep into the supervised learning and in particular, a regression problem. So let's remind ourselves about the general framework of machine learning. So a machine learning is to learn from experience. So you have some experience. And you have some machine learning algorithm. It gives you some model that maps from input space, some sample in the input space, to some sample in the output space. Okay, so this is the learning and training. This is step one, or stage one. And stage two is you would like to apply this machine, this function, this model to some input, okay, to some possibly new input. Okay, you have some new input, and now you get a prediction. So this is the general framework of machine learning. So regarding supervised learning, we mentioned that supervised learning is usually you have a specific goal of prediction. So let's talk about how to formulate a supervised learning task. So, we are dealing with samples or data instances. So one data instance is usually a piece of experience. And one example is the box example. So I still have, and I can measure the size of the animal. I can measure the fur of the animal, and I can also weigh the animal. How heavy is the animal? So I have a lot of boxes, and there are different animals. So supervised learning says usually you have a specific goal of prediction. For example, my task is to predict the weight. Okay, task is to predict. Maybe this is my first task, to predict the weight based on size of fur. Okay, so this is one of my tasks, and I can do the other thing. For example, I can predict, or maybe to predict the size based on maybe weight and fur. It's also possible, right? So you can define different tasks, and there are different tasks. So you have to have a specific goal of your prediction, and that forms one of the tasks. To formulate it a little bit more, the task of supervised learning is really to predict something based on something, okay? So I'm saying to predict the target, based on some input, okay? So in task one, then, the weight is my target. The size and the fur are input, so you have two input. And in task two, then the size is the target, and the weight and fur, they are input, okay? So I can say in supervised learning, we are provided with some input. Okay. And this input is known during both training and inference. Okay. So just here, so I'm provided with some input or features or some representation of my data, and I also have the target. So this input is known during both training and prediction, okay? And we call it X. So we denote it as X, okay? So X can be some features about the data sample. And usually we have multiple features. So one feature is not enough. For example, you cannot really predict how much an animal weighs based on its size only. You have to also know what animal it is. And this can be, how does the fur feel like? Then you know what kind of animal, and then you can more accurately predict the weight of an animal. So usually X has multiple features. So in this case, X is known as a vector. sometimes in printed matter, we have bold letter to represent X, right? So for example, I say X1 is the first feature, X2 is the second feature, so on and so forth. Maybe I have D features in total. So I can stack all the features together and I make it a sequence of features, so it becomes a vector. So in print matter, we usually have a bold letter to represent, to represent a vector like this. So suppose each of the feature is a real number, then we'll have a d-dimensional vector like this. So this is the input, or sometimes it's also called the features. So as an input, a feature may be either categorical or maybe it's a real number. So if a feature is a real number, if a feature is real number, for example, how large it is, then it's easy. So the X is just the value of this variable. So if a feature, then, so xi in R is just the value of the feature, okay? So if a feature is a categorical variable, what happens? For example, I would still like to predict the weight of an animal, but now this time I know what animal it is. It can be either a cat or a dog or an elephant, okay? For example, a feature, either an animal, the type of the animal, and it can be either a cat or a dog or an elephant, okay? So how can I represent this feature? So maybe I can say this is 1, this is 2, and this is 3, okay? Or maybe I can say this is 3 and this is 1, this is still 2 and this is 1, okay? Now you see some problem. So if you are representing a categorical variable by like integers, for example, 1, 2, 3, then you are implicitly saying dog is twice as much as a cat, right? When you do computation, when you do numerical computation, it's twice as much as a cat. Then elephant is 3 times as much as a cat. And also, the difference between cat and dog is the same as the difference between elephant and dog. So that is confusing. And this is highly dependent on how you label the categories. So I can also label it 3, 2, 1. So now this time I'm implicitly saying, cat is actually 3 times larger or 3 times more in some feature than the elephant. And dog is twice as much as an elephant. So in this case, you are implicitly giving some metrics to the space, to the features. So it's not the nature of the categories themselves. And also it highly depends on the labeling of these categories. So this is not a good way. Not good. So representing a categorical variable by integers is not good. So another way of representing a categorical variable is one-hot representation. So I can expand this feature to 3 dimensions. So this is some x1, x2, x3. And each of the dimension is actually 0 and 1. Okay, it can be either 0 or 1. And of course, 0 and 1 are still real numbers. So it's still real number like this, okay? It's still real number, but it's a subset of the real number. It can be either 0 or 1. Then I will say the meaning of the first feature is whether it is a cat, okay? The meaning of the second feature is whether it's a dog. Or the meaning of the third feature is whether it's an elephant. So now you see, if it's indeed a dog, then the feature would be 0, 1, 0. If it's instead a cat, then it will be 1, 0, 0, or elephant, 1, 0, 0, 1. So this is the feature of a cat. This is a dog. This is a, elephant. Okay. So now in this case, I'm representing a categorical variable or a categorical feature as a set of numbers, okay, as a sequence of numbers. And each number is binary, it's either 0 or 1, okay? And you can define the semantics of 0 or 1 is symmetric, so there's no particular reason whether it's satisfied should be 0 or 1. But usually, by convention, we say if it's satisfied, then it's 1. For any animal, it can be either a cat or a dog or an elephant, so it's one hot. So you will not have something like this feature is invalid to represent the animal. It says it's both a cat and an elephant. It's impossible. So this is invalid. But you can only have one element armed in one data sample. So it's one hot. Okay, so this is the one hot representation of a categorical feature, which is good. So this is better than the integer representation. So in the integer representation, it's no good. And of course, this feature can be concatenated with some other features, right? So I can say I have 3 features. One feature is the size, and the other feature is the fur, and the third feature is the category, whether it's an animal or not. So my actual representation will be, for example, for some animal like this animal, the size is small, maybe the size is small. So it's not necessarily 0 or 1, it can be, for example, 2. It's still small, 2. The fur is soft, and the animal is actually a cat. I know it's a cat, so it's a cat. So it's 0, 1, 0, 0, okay? And now you can represent this animal according to these features as a 5-dimensional vector. So this categorical feature expanded into 3 dimensions, and each of the dimension is either 0 and 1, but there's only one element being armed, and then you can make it a 5-dimensional space. Okay, so this is input of supervised learning. Then how about output? The output of supervised learning, or sometimes also known as the target, I call it T. Okay. And we mentioned in this course, we mainly talk about individual predictions. We don't consider a sequence of labels, a set of labels. So we only consider one label at a time. So the T is a single number, and this is a real number. So that is regression. So if the output is a real number, then it's regression. Or if T is in some set, for example, C1, C2, up to Cn, for a finite set, then it's classification. Okay, so at this moment, we'll zoom in a little bit more into the regression. So this will be later. Okay, so a regression problem is indeed a supervised learning task where the output is a real number. Okay, but the input can be either real or categorical, and when you represent the categorical into a one-hot feature, it's still a subset of the real, so it's still real. So a regression model, so sometimes I call it H, okay? So H is known as the hypothesis. A regression model is indeed mapping from the input space, which is RD, to a real number, AR, okay? Where D is the input dimension. And during training, as I mentioned, you usually have many pieces of experience. So each of the piece of experience during training, each piece of experience, we call it a data sample or data instance, or maybe data point. They're just standard terminologies. For each piece of the experience, it looks like this. It's an input X, so it's bold, it's a vector. Sometimes I put a bar underneath the ladder, but sometimes I just ignore that. So this is input, and this is the target. So each of the piece of experience look like this. Okay, this is one data sample. But how about my training set? So my training set is a set of experiences. So a set of experiences. Okay, for nth experience, I denote it as X superscript M and T superscript M, okay? So the X is input for each of the X, it's a vector. And then by saying vector, we usually mean it's a column vector. So you think of it's a very ugly stuff, you know, X1 M, X2 M, up to XDM. If you think of every vector is a column vector, then you will not get confused of the dimension of like vector matrix multiplication. So every vector is a column vector by our convention. Okay, so each data sample looks like this. Then my entire training set is maybe my first data sample, my second data sample up to my capital Nth data sample. Okay, which is denoted by, we have a short notation for that. I can call it X little m, T little m, where m starts from 1 up to capital N. Okay, so I just denote it by this shorthand notation. So where m is the number of, where m is the total number of experience, or the number of samples, training samples. Okay, so now we are clearer about the supervised learning task. So the experience is a set of instances. And for each instance, I'm provided with its label. I'm provided with its feature and its label, okay? And then I learn a machine learning model. So suppose this is in R to the D, and TM is in R. And apply the machine learning algorithm. It gives me a model that maps from R to the D to the R. And this is my training. And during prediction, I would just like to apply this model here. And I have a new sample, okay? A new sample, X star M. So I just call it X star. So this is my new sample. New sample. Or maybe you have many, so you have a set of new samples. So I would say this is X star M, maybe M from 1 to maybe some other number. So I call it capital M test, but this is ugly, but it doesn't mind. So I have a set of new samples. Maybe some of the samples overlaps with your existing experience, but it doesn't matter. So some of the samples. And then you apply your model to each of the samples. You are not applying your model to the set, but to each of the samples. Okay, so each of the sample is R to the D. Then I make a prediction. So I make a prediction. So I call it T hat M. So hat is usually some prediction. Okay, so this is not the true label or the true target of this data sample. Sometimes I make an error. Maybe the animal weighs maybe 2 pounds, but I now predict 1.8 pounds. It's also possible. So if you have M samples for the test or for the prediction, then you also have that many labels predicted. So just a quick note, the restriction that the input is a d-dimensional vector is not necessarily the case for other machine learning models. So in practice, you can define many fancy machine learning models, and then you can deal with trees, you can deal with the graphs, or you can deal with many things. Or sentence, I'm doing natural language processing, you can have a sentence. And it's very in length. Some sentence may be short, some sentence may be long. It's not a fixed dimensional signal. As a starting point for a general start, in this course, we mainly focus on the fixed dimensional input, just like a d-dimensional space. It can be real valued. It can also be categorical. So you expand it as a one-hot representation. So we are now clear about what is a machine learning task or what is a supervised learning system. So I think we are clear about these parts. So we know what is training set. How about what is the learned model, and how can we use the learned model to make a prediction? This is also known as the hypothesis. So what is still mysterious is about the machine learning algorithm. So what happens here, and why is it even possible to choose a function that works for the task? So our next goal is to formulate a machine learning system, especially in the setting of supervised learning, okay? Or maybe regression. So there are a few steps for if you want to build a machine learning. So contrary to some of our intuition, the first step of machine learning is for humans. So humans define all the possible candidate hypotheses or the model, candidate models. Still standard to call it hypothesis that a machine learning system can choose. Okay. So this may appear very counterintuitive because machine learning starts from humans. So I have to tell the model, here are some functions that I would prefer. And the machine chooses a particular function from the candidate set and say this fits best for the training set. So this set is known as the hypothesis set, denoted as script H. Okay, so H is a set of functions that maps from your input to your output. Okay, so output may be Y, so sometimes, so I just call it Y. So the hypothesis set is usually a subset of functions that maps input to your output. So this is usually a subset, and this is usually a very, very small subset. So now we have a question, why we must do that? Why must we must work with a hypothesis set that is a strict subset of all functions, or it's even a very small strict subset of all functions? So we will leave the question in a minute. So the second step is still humans, okay? The second step is humans define a criteria that the machine would evaluate the candidate functions in H, okay? So eventually the machine picks the best function in H. So this H, so the machine, after machine learning, the machine learning system suggests you a hypothesis, which is some criteria. So I call this criteria J, and usually we minimize something. So this is also known as the objective. Okay, so usually when we do optimization, it's sometimes standard to say I minimize something. When you want to maximize something, you can minimize the negative of that, right? So we say argument is to minimize J of H, okay? Where H is in my hypothesis. Okay, so given the hypothesis, I have a criteria, I have a fitness or have a goodness of this function or the badness. Okay, I want to minimize the badness. So if you minimize something, it's also known as loss. We have a lot of terminologies, but they're just standard. Okay. And this criteria is based on my training set. So we know we have some experience and we have a set of experience and they are my training set. So this criteria is a function of one particular hypothesis in my hypothesis set. And also it's a function on my training set. Okay. Okay. So now the next step, I would say the next step is minimizing. So I would say the third step is machine picks a hypothesis H in my hypothesis set, hypothesis class. Okay. So I think it's more standard to call it hypothesis class. And I would make a note saying J is a function of H and my training set. So the first two steps of machine learning starts from humans. So we first define what are the all possible functions that the machine learning system can pick. And the second step, the human further define a criterion that how the machine should pick the function. And the third step, now it comes to the machine side, and the machine will pick a hypothesis H in the hypothesis class, okay? According to some criteria, which is a function of the hypothesis itself, as well as the training data. So now this is the first step, training. And the second stage is inference. So given some unseen data, so given some maybe tested data, but usually the test data is unseen. If it's seen, then it's just the training data. So maybe there are a few samples are overlapping, but usually it's not overlapping with your training. So given some unseen data set, then the machine applies H, okay, to any sample X in my unseen data and makes a prediction, okay? Then I would evaluate my machine learning system, whether it's good or not. So we evaluate the H is evaluated by, so this criteria may be the same as this criteria, but maybe different, and usually they are different. So H is measured by some other criteria. This is called measure of success. Okay, whether my machine learning model is successful or not. Some other criteria, which is called measure of success, but we also call it error. Also called error. Okay, and I plan to use this terminology in this course. In the last term, I use measure of success, but it's confusing whether I should maximize the measure of success or minimize the measure of success. So now I call it error. So, error is a bad thing. So we would like to minimize error, okay? So H is evaluated by some other criteria, which is the error, which is a function, of course. Now, error is a function of course, on the D unseen H, D unseen, okay? Okay, very good. So basically, this is the framework of a machine learning system or a supervised learning system. This is a very standard system and it's very proper. And sometimes you can even develop some, improper systems. Like, for example, my H is not in my hypothesis class. So I give you a candidate function, but eventually I deviate from the suggestion and pick some other function. Does it matter? No, because our ultimate goal is to make a prediction. I don't mind what is my function. So it's also possible, and that's called improper learning, but that's complicated. So in this course, we only focus on the framework like this, okay? Humans give a hypothesis class and a selection criteria, and the machine learning system picks a function in the hypothesis class according to the criterion, according to the training criterion, which is the function of the hypothesis class itself, as well as the training set. Now, in the test phase, so they are training. And in the test phase, we are given some unseen data. And then now in the test phase, we are given some unseen data, and I have some other criteria, and maybe the same criteria, maybe different, which is known as the measure of success, or also known as error, which is a function of your hypothesis, as well as the unseen data, okay? So this unseen data is almost always different from your training data. It's extremely unlikely that they are exactly the same. So maybe very few samples are the same, but usually they are very different, okay? So now it seems like machine learning is not a mystery, because if you have training set is similar to the unseen data set, and if you know your J of H, J is also similar to your error, then if you can optimize J to a very large extent, then you can also optimize E, right? Then you must perform very well on E. This is almost the story, except that you have to be very careful about the hypothesis class. So I left a question here. Why do we have to specify a hypothesis class? Is it possible that we don't state our preference and we let the machine to learn itself? So now my argument is, if humans have no preference, any function f that maps X input space to Y space, does this set exist? Yes, the set exists. Okay, yes. So have no preference on the function, on all the function, on any function, then machine learning is impossible. Okay, if we don't have any preference, or maybe I restrict the candidate hypothesis, or maybe I still allow you to select from all the functions, but I would prefer put more emphasis on some of the functions, like give a higher probability or higher weight, and it's more likely to choose those functions. Then learning may be feasible. But if we don't state anything, then learning is impossible. So example. How about my training set is like this? Okay, it's 1. So this is X. So X is one-dimensional space, X is R, and Y is also R. So the input is a real number and the output is also a real number. So I have some samples like this, 1, 2, 2, 3, okay, so and so forth. So I have a few samples, okay. These are all my samples. Then I don't have any restriction on the functions, on the hypothesis, or I have no preference. So I consider a subset of the functions. So I consider all the functions fa is such that if x is 1, 2, 3, 4, or 5, or I call it a otherwise. You know, x is a real number. So fa is a function from R to the R itself, and then I define fa like this. Then, you know, all the functions look like this. A is a real number. A itself is a real number. So I have a set of functions. This set of function is definitely a subset of all functions that maps x from y, right? But I could say this function is too powerful. So what I got a little bit confused here was not fa too powerful, but rather all the functions are too powerful. And in particular, this very powerful set contains these functions, and we will show it makes machine learning infeasible. So what happens? So for NAA, the training loss or the training criteria or the selection criteria of my hypothesis HA and my training set, okay, it's the same. So it's a constant. Okay, so I have no preference. It's a constant. And my selection criteria is only on your training set. You don't know anything about your test phase or your prediction phase or on the unseen data. You know nothing about that. But since our hypothesis here is saying I don't have any preference on that, I would like the machine learning algorithm to learn the preference over all functions by itself. Then it has no preference. It says, okay, they are all good, all good. But then in terms of prediction, now it's a disaster, right? So in prediction, it's a disaster. So now it says, maybe my test set, my unseen sample is here, maybe 2.5. And this is X, and Y maybe 2.6, right? So now maybe sum of A, you know, if A is 2, then reasonably fine, right? Reasonably good, good. So it's not perfect. You still have 0.5 difference, but it's good. But what if, you know, it has no preference on NA? What if A is 1 million or maybe 10 million? It's a disaster. Or maybe A can be minus, right? You know, 1 billion to the power of 1 billion, or even to the power of 1 billion. It's a disaster, but you have no preference, right? The hypothesis here is we have no preference on which function that the machine learning can pick. Now the machine learning evaluated some functions, at least here a subset of the functions, and they're equally good, right? They're equally good. Or maybe I can still define it clearer as saying the J of a particular sample. So for the mth sample, Jm is my difference, you know, the absolute difference, or maybe square difference of your hypothesis applied to this sample and the difference between its sample, right? Or maybe I can make it square. And then my total loss, or the total objective, is the average over the individual samples, right? So now you say, if you have this function, it's all good. It's all good. All the functions have 0 loss, right? And it's the minimum loss. It's all good. But eventually, when you do a prediction, you know, the prediction is arbitrary. So what's wrong with it? So that's why we have to state our preference first. It must be a very strong preference. You have to rule out many, many functions that you don't like. And you say, this is my subset of functions. This is a very selective subset of functions that I would like to try. And now the machine learning evaluates the functions on the training set. And as long as some of the functions, among not too many, gives you good results, then you can reasonably expect that it will give you good results on the test set or on the unseen set, right? So this is the intuition why machine learning is still feasible. So such preference is known as inductive bias. So this is oftentimes misinterpreted, but the standard meaning of inductive bias is before you learn the model, before you train the model, you have to state your preference. So this is the bias of the machine learning model, which is induced by humans. We tell the machine that we have some bias. Now the machine take the bias and evaluate the function, and eventually the machine can learn. Otherwise, machine learning is infeasible. So this is just some high level intuition. If you feel interested, you can take a closer look into the PEG learnability, which is probably approximately correct learning. We will not cover the theory in this course, but I just give you some intuition that why machine learning is working and how well it can generalize from the training set to the unseen set. So another quick thought, what if my hypothesis is just FA? Is learning still feasible? So, you know, given the data, and I define FA, even FA, the set of FA is a very restricted set in all functions, but the learning is still infeasible here. It's still, you know, the prediction is still arbitrary for the unseen, but the model performs well on training set. What is wrong here? So the problem is, as I mentioned, in machine learning, you must state your hypothesis class first. You first have your hypothesis class, and then you are given the data. So this is the wrong way of doing this. It should be define your hypothesis class first, and then you are given some data, okay, given some data. So if you work in this way, then data are randomly generated. It's highly unlikely that if you still have these functions, it's highly unlikely your data samples are precisely 1, 2, 3, 4, 5. Maybe some samples are here and some samples are there. It's a more typical sample, right? Because you don't know the data, then you cannot foresee what the data will be. Then in most cases, you cannot perform very well on the training set. So training is infeasible. So it's also expected that you cannot work well on the unseen data set. So it's almost like probably. So by probably, I'm saying it's unlikely that you happen to know this. Okay, probably, approximately. Of course, I can guarantee that my model generally work well, but I cannot guarantee that my model work well for each data sample. Okay, even probably. So probably, approximately, working very well. So correct. So usually, we have learned some lesson. If we have no preference on all the functions, then learning is infeasible. I mean, you can say meaningful learning. So after learning, the prediction can be arbitrary. So meaningful learning is infeasible. If it's powerful, if my hypothesis class contains too many hypotheses, then you can definitely fit the training set better. The selected edge can fit your training set better. Okay, but it may not perform as well on the unseen. So on the unseen data set, it will not be so good as the training set, right? If edge is less powerful just means it contains fewer functions, then edge fits worse, detrained worse, but the gap between the performance of edge on detrained and the unseen is smaller, right? So if I have a very large hypothesis class, then I may have some peculiar function that fits the noise of my training set. But then such noise does not generalize to unseen set, right? It doesn't, it's not the nature of your data set, then it doesn't apply to unseen data set. So you may expect a huge gap between the performance on the training set and on the unseen set. But if edge is smaller, then I don't have that many functions. Then as long as some of my function can fit your training set well, then it can reasonably perform well on your unseen data set. So this is a very quick introduction about overfitting and underfitting, and we will come to the issue later. We will discuss it in great detail, but this is the first impression that if you don't state your preference, then it's the extreme case of overfitting. So if you don't state it's an extreme case of overfitting. Okay, so now we would apply we will give an example of this framework. So example. Finite hypothesis class. Okay, so we have two machine learning systems. Machine learning system 1, machine learning system 2. So by finite hypothesis class, I mean I only have finite number of hypotheses in the set, okay, in the script edge. So my edge, the first machine learning system is H1 and H2. And my second edge, okay, before defining the system, I have to tell you what is the task. So the task is to input is a real number and the output is also a real number. Okay, it's not surprising. So in here, both H1 and H2 are functions from R to R, and H2 is 3, 4, okay? And I have some silly functions. H1 is all 0. Is that a function? Yes. H1 of X is 0, okay? And H2 of X is minus 10,000. Is that a function? Yes, it's a function. So H3 is of X is X, okay? Is that a function? Yes. H4 of X is maybe X cubic, okay? So all of them are functions. So selection criterion, J, so this is H1, J1 is a function of H and also my training set. So suppose my training set has M samples. So I will say, how about I sum over all kinds of samples such that for each sample, I'm considering the absolute difference, maybe the H of my X of M and the target of M, the absolute difference between my prediction and my target. So this is my training criterion for my first machine learning system. And my second machine learning system, I do something like this. Okay, is that a function? Yes, it's a function of my H. H is here. It's also a function of my training set. So these are my machine learning systems, and I define the machine learning system in advance. Now I have my training set. So my training set is indeed this stuff. Okay, I have 3 points, x1, x2, and x3, and they are 1, 2, 3, and y is also 1, 2, 3, oh, sorry, 0, 1, 2, and y is also 0, 1, 2. Okay, so these are my training set. The training set is not a line, the training set is samples. So it's these 3 samples, okay? So these are human does, and this is the task. I cannot change my data set. So the machine says I would pick H1 is argument of H in H, J1 of H, D train. And here H2 is argument, of course. So this is H1 and this is H2. Okay, optimization algorithm is by enumeration because we only have finite hypothesis cards. So we can just enumerate them. Okay, it's the same. So it's also enumeration. So I can try both things. So how about J1 of H1? So I omit the train. So what is that? I mean, it's the absolute value. So now it's 0. You don't have anything for the first sample. And now it's 1 and it's 2. So it should be 3. And then average by 3. Okay, how about I don't average them. So it seems simpler. So how about J1 of H2? So it's a very large number. So you first have 10,000 and then you have 1 plus 2. So it's, and you have 3 samples. So it's 30,000 and you have 1 and 2. So it's 03. Okay. So now, you know, H1 wins. So pick my hypothesis as H1. Right. So how about this? J2 of H3 So what is H3? H3 is X, okay? You know, it fits very well, it's 0. Okay, sorry. So how about J3? J3 is X, okay? It looks very well. Okay, but my confusion here was I was meant to have X. So I would like to ignore T, but I only have X. So suppose we are working with this equation, then J2 of X3 is, so now I'm very slow. So J2 of X3 is, okay, the target is 0. So this term is 0, 1, and 8. So now you subtract it with 0, 1, and 2, you get 6. Okay. And J2 of H4 is, so H4 is, you know, X cubic, and you subtract it by H cubic, it gives you 0. So pick H4. So unfortunately, it seems like you have a very good function here, but due to your bad selection criterion, sometimes you get a very bad result, okay? So this is my training phase. What happens with the test phase? So now test phase, I'm provided with the D on scene. So D on scene, we assume it's 5 and 5. Okay, so X is this and target is this. So now we would like to evaluate the measure of success, which is the error. Error is usually on my unseen set. So error of H1 on this D unseen, but I can omit D unseen, is, okay, I didn't mention what is error. So I tell you the measure of success is, error is the sum of samples, okay? Then have the same criteria as the first machine learning system. So it should be h of x m minus t m. Okay, the target, which is my new samples. Okay, the absolute value between the target and your predicted value. So this is my error. So what is the error for H1? So the error is 5, right? 5 is here. But I'm picking H1. H1 is all 0, okay? So it's 3, 4, 5. So the error is 5 for H1. So what is the error for H3? H4, okay? The second machine learning system picks H4. So what is the error for that? So the H4 says I will take the cubic. So 5 to the cubic. So 5 cubic is 125. So the error for H4 for the second machine learning system is 125. So we have a conclusion that, okay, machine learning system 1 wins, okay? So this shows, even if you have a very good function, if you have bad selection criteria, or you have some other things mess up, then you may not get very good results, okay? So this is really a silly example. It's a toy example, but the finite hypothesis class. But it shows very important components of a machine learning system. Okay, we have the training, we have the test. But in the training, or even before training, we have to specify the hypothesis class. And then we have to tell the selection criteria. And then the machine learning will optimize it to me. Okay, and I apply the selected hypothesis to some unseen data. After that, I have the error or measure of success. Then eventually, maybe I have to compare a few systems. Then I know some system is better than the other. So less than many. But some other criteria, maybe probability, which will be widely used in the future of this course, is not an essential component of machine learning. So we can do machine learning without probability. And sometimes probability hurts because probability is a very strong constraint. And sometimes we want to get rid of probabilities, but it's not necessary in the first place. But here, the components here are almost all necessary. So lessons learned. A machine learning system involves, what do we have? Involves humans. It involves humans. Specify what is the hypothesis class, what is the selection criteria, and what is my optimization algorithm. I haven't given much example here because it's simple, it's finite hypothesis class. And also maybe you are also possible to collect the training set. Okay, you can adjust your training set. Maybe you can add something. But we cannot control the test set or the unseen set, which is when your machine learning is deployed, then what are the data? So it's out of our control. And also we cannot define the measure of success, okay? So the measure of success, for example, so we want to earn some money, so we go to the stock market. The success of a person is measured by how much money they earn. In stock market, it's not in universities. But now you say, maybe I would like to change the measure of success. So I would say the measure of success is how many marks do I earn in stock market, right? It doesn't make sense. So it's not a real success. So in that place, the measure of success is how much money you earn. You say you earn marks, you earn good grades, letter grades. It doesn't make sense in the stock market. It makes sense in universities, right? So if you go to the stock market and say, okay, I'm earning a high grade, you know, it's not a success. It's a success in spirit, but it's not a real success. Sometimes the measure of success is subjective as well. For example, I want to do machine translation and I want to evaluate the translated text automatically. So I have some measures. So the measure is imperfect because nobody can tell whether a sentence is good or not. It's another machine learning problem. It's imperfect. But the design of the measure of success should be independent of your machine learning system. Right? If they're dependent, then you know what happens. The machine learning system just do some random output or do some arbitrary output, and the measure of success is okay, you're good. Then the machine learning is meaningless, right? When you deploy your machine learning system in the real world scenario, you still lose a lot of money, right? So that's why these things are not what we can control, but these are my design choices. Okay, good, thanks.